VC chemistry, electrolysis of aqueous solution. So in this session, we'll tackle with another relatively inexpensive electrolysis technique to produce substance. However, in a lot of cases, this technique will invite some problems. Okay, so let's revise our memory as a comparison between galvanic cell and electrolytic cell. So one produces energy, electricity, and the other one consumes it. Galvanic cell utilizes a spontaneous reaction and convert chemical energy into electrical energy. Electrolytic cell does exactly the opposite. It converts electrical energy back to chemical energy through a non-spontaneous reaction. As compared to these, the location of anode and cathode, because of this definition and because of the reactions are reversed, so in galvanic cells, anode is at the negative end, where when you recharge it, anode goes to the positive end. Okay? Now, from the study design, we need to be able to use electrochemical series to explain or predict the products of a electrolysis, especially when there is competition. Okay, so that's our electrochemical series. Just as a revision, your top left is your strong oxidants. They like to go through reduction. So the higher top left you are, the more likely you are going to win the competition and go through a reduction reaction. So it goes forward, gains electrons. And the lower right is the stronger reductants. Okay? So the more lower right you are, the more likely you can win the competition and loses electrons in your reaction and goes backwards. Okay? So in whatever reaction, it is always the stronger oxidant prioritized to go through a forward reaction, and it's always the stronger reductants being prioritized to go through an oxidation, so it goes backward reaction. Okay. So remember that we in electrolysis of molten NaCl, right? We have a non-spontaneous reaction. Energy is provided. At the negative end, the sodium cation is going through reduction to become sodium, and the positive end of the electrode, chloride is being attracted by the positive end of the power supply, and therefore it goes through oxidation. So your electrons flow from the negative end of power supply, go to the cell, and come back to the positive end. And in this case, when we are electrolyzing a molten sodium chloride, there are only two species to participate in the reaction. That is sodium and chloride ions. Okay, there's nothing else. But when an aqueous solution is used instead of a molten electrolyte, then water is a third-party reactant because it is a solvent. That water also exists in that whole reaction system, in addition to the cations and anions that dissolves in it. So, for example, if we electrolyze sodium chloride solution, in our reaction liquid, there is sodium cation and chloride anion, but also water exists on both electrodes because it's the big giant solvent, right? It's like the pool. So on your electrochemical series, water can also be reduced to become hydrogen gas. Water can also be oxidized to become oxygen. Now, this is where water can gain or lose electrons depending where it is at. And because of these two reactions, our half equations at the cathode and the anode becomes more complicated. Now let's have a look. Why do we mean it becomes more complicated? So now, this is still a electrolytic cell. It is sodium chloride solution now. So we have water, sodium cation, and chloride anion. Let's look at the negative end of this electrolytic cell. So at the negative electrode, electrons are being supplied to the electrode. In the solution, what are the species that can actually gain electrons? You notice that sodium cation can definitely gain electrons to become sodium solid. Yeah? This is not molten liquid, so it's a sodium solid being produced. But at the same time, water can also gain electrons to become hydrogen gas. Now, if you have two species that can gain electrons, which one is going to be prioritized? Remember, we say it's always the top left that is with a larger E value that is going to be prioritized and go through reduction reaction, goes forward. So, since water has a stronger oxidizing strength, it's more likely to gain electrons and being reduced. And therefore, water is gaining electrons out of this competition rather than sodium gaining electrons. So sodium cation is just going to stay there because water is always ahead of it. Okay? And as a result, on your negative electrode, you're not really producing sodium metal. Instead, you're producing hydrogen gas. On the other hand, on the positive electrode, electrons are leaving to go back to the power source. So there should be an oxidation reaction happening here. So what are the species that can actually lose electrons on this electrode? You notice chloride can totally lose electrons and become chlorine gas with an E value of 1.36 and it's positive. Okay? But at the same time, water can also lose electrons to produce oxygen gas. And water's oxidation reaction has a lower E value as compared to chloride. Remember, we said if you are going to go through oxidation, you got to go find the stronger reductant. The bottom right is the stronger reductant. That is water rather than chloride ion. So, again, as a result, the stronger reductant goes through oxidation, losing electrons, and therefore, instead of producing chlorine gas, we're actually producing oxygen gas. So water, again, wins the competition. Now, when you put these two reactions together, you'd notice that, hey, you started out to electrolyze sodium chloride solution. However, somehow it turns into an electrolysis of water because both anode and cathode, water wins the competition. At anode, it is the stronger reductant, this one, okay? And at cathode, it is the stronger oxidant that goes forward, okay? So overall reaction, if you add them together, you'll notice that it becomes water being electrolyzed to hydrogen gas and oxygen gas. And this is where what we meant by water competes with the solute, which is sodium chloride, and it is being electrolyzed instead. That is the competition at electrodes introduced by this third species in an aqueous solution.